So the next talk is from Linda Broadbelt from Northwestern University on modeling or predictive analyses.
Okay, thank you very much for the invitation to speak in this session. And I'm just going to try to give really a broad overview of a variety of different computational approaches, modeling and data science-based predictive methods that can be utilized to address the problems that we've been talking about in the last 2 days. And so I'm going to go through a couple of vignettes to set the stage for the work that we've done in this area, but really the intent is to give you an overview of various methods. So early on, we were thinking about how could we exploit polymer pyrolysis as a tertiary recycling strategy. So heating polymers up in the absence of oxygen to high temperature in order to degrade them back to fuels and chemicals. We also have thought about this idea of compatibilization, and this was the looking at can you design polymer backbones in order to be additives that you could add to compatibilize dissimilar polymers. And so this was work in which we looked at gradient copolymers. So this builds on some of the stuff that Megan was talking about yesterday. And in this case, the method that we were using was kinetic Monte Carlo, in which we could very explicitly know exactly how the monomers were arranged along the length of the polymer. So even though the overall composition of the polymer might be the same, the arrangement might be very different. This impacted the ability to act as compatibilizers, but thinking about designing for recycling, you can imagine that sequence might matter here of catalytic strategies that you could access to decompose polymers. And then finally, I'm loath to use the word bioprivilege because it got a laugh earlier this morning, but we are going to talk about how we can access techniques for mining molecules and looking for bioprivileged molecules, and in this context thinking about designing new monomers and polymers that can be used for degradation, but also in the context of the specific project that we have related to looking at new flame retardants. And it was mentioned yesterday that maybe we could think about those flame retardants for easy separation or recyclability. So those are really 3 stories. I'll go into 2 of them, but basically what I want you to think about is that these all have a common thread. They're very complex reaction systems. Many hundreds of thousands of reactions and species might be relevant for the reaction network, and so we'll put together a platform of how we can build up these very detailed models. So just to get you thinking about what I mean when I say a model or a reaction network description, you can imagine that there are what are called lump models, where people just say polystyrene goes to products, and we just have an overall reaction or a rate constant and rate constant that represents them. So these are species, and the coefficients are lumped quantities. There's also what are called pathways level models. The difference here is that you're at least trying to trace how you might go from a polymer to now molecules rather than just product lumps, and so that's shown here. And still the species are molecules, but the rate coefficients are lumped quantities. Where we really try to focus our attention, and this sets the foundation for what Paul Dauenhauer talked about yesterday of the atomic scale description that could feed into reactor models, would be mechanistic models. So in this case, we're trying to go from a reactant to a variety of different products, but also knowing what intermediates via those intermediates, and therefore the species are radicals or other intermediates relevant to the chemistry and molecules, and the rate coefficients describe elementary steps. And that's advantageous to us because now we can access theoretical calculations to get at those rate coefficients. So just to give you a sense of the kinds of systems, and this is not great viewability, but we're going to formulate then reaction mechanisms, detailed reaction mechanisms based on what is called the reaction family approach. So you say, if I'm going to look at polystyrene or polypropylene or polyethylene degrading at high temperature, thermolysis, no oxygen, then this is free radical chemistry that was mentioned yesterday. And there are certain types of reactions that are accessible at these temperatures when there's free radical chemistry. So their bonds can break, depolymerization, the reverse of polymerization can happen, but then there are all these other side reactions. So hydride transfer, so chains can interact and abstract hydrogen. There is recombination that was brought up yesterday, but at these temperatures that will compete with other reaction families. There is backbiting, so even if the chain's nicely depolymerizing, it might backbite and put the radical in a different position, and then you're not getting monomer anymore. So all of these reactions are put together in order to form the foundation of the pyrolysis of these hydrocarbon-based polymers. And then we need rate coefficients. So we need, if we're going to have all of these reactions, there are thousands of them, we put together a hierarchical estimation of rate coefficients. If someone's measured an experimental value, we love NIST because they go and often measure individual rate coefficients. We will use those. But usually for all the reactions that are not available, those are not available, so we'll use the methods of transition state theory in order to estimate them computationally. But you're not going to do 1,000 transition state theory calculations on the fly. So usually what we'll do is a selected number of calculations, build up structure reactivity relationships where you can relate kinetics to something that's easier to estimate or measure, like thermodynamics. And so then we'll have a hierarchy for getting at thermodynamic properties as well. But in the end, then we're putting together a formulation of a platform for estimating all the rate coefficients in the model. Well, then you need the design equations. So Paul talked about this a little bit yesterday. You need the design equations that now mimic the reactor in which you're carrying out the reactions. And so in this case, this was a simple batch reactor. So these were meant to be experiments that were to get at the intrinsic kinetics and not layer on all of the complexities that Paul talked about yesterday with aerosol ejection and solid and temperature gradients. But so we put together the equations that describe the decomposition of polymer into oligomers. So we're monitoring the molecular weight decay, but we're also monitoring the evolution of small products. So remember, the goal here was pyrolysis for fuels and chemicals. So we want those small molecules, the monomers, monomers or small molecules that are formed. So we have the foundation based on this moment-based continuum model. We've got everything, and these are the kinds of results that we can get. So walking you through, this is a platform then that was applied to a variety of different homopolymer degradations. So polystyrene shown on the upper left, and that was looking at molecular weight decay, but then also the evolution of the total molecular, low molecular weight products. How much dimer are you making? How much trimer are you making as a function of conditions? Applied that also to polypropylene. A little hard to see here, but the product distribution's getting more complex now because we have lots of different chain lengths that are possible. So you have a lot more different hydrocarbons. The one on the bottom left was interesting in the sense that you might think, okay, I have a polystyrene, I have a polypropylene model, I just need to now marry them, provide some kinetic coupling between the two, and I'll be able to predict the behavior of the mixtures. But these are two immiscible polymers, and so even at the temperatures that we were doing these reactions, they weren't just the concatenation of the two single components and the interactions. So we even had to take into account some phase behavior and interfacial area between the polymers to describe that. And then finally on the lower right, that looks a little like Susanna had a plot of polyethylene degradation that was more catalytic, of kind of a broad distribution of molecular weight compounds, and that's what's shown on the bottom right for polyethylene. And so basically we have the ability to look at a wide variety of decomposition of polymers. But free radicals are really not that attractive, so you don't have a lot of control over what the product distribution looks like. And so you have temperature and you have some pressure concentration handles, But really, we'd like to think about applying methodologies that could think about catalytic strategies that were also mentioned yesterday. And I don't have a specific example in the thermoplastic regime, but just to show you an example here in work that we did related to cellulose decomposition, because cellulose is just a polymer. Then this is looking at carbohydrate active enzymes. This is actually work that a student of mine, Heather Mays, did in collaboration with Greg Beckham and his team, of thinking about, can we use methods that start to look at the depolymerization and mimic nature? And this is a movie, but I'm not sure it's going to play. Oh, okay. So in this case, we're looking at the cleavage, this very selective cleavage of that glycosidic bond. Oh, did not play. In this case, this is now using a totally different kind of modeling. This is ab initio molecular dynamics, where, let's see if it's going to play, where we're actually monitoring reaction mechanisms. So you're figuring out how the enzyme acts, and you're even getting at kinetics. So you can, sorry, it didn't play, but it actually gives you then the barrier, and you're able to actually extract kinetic parameters from that simulation. So the thinking here would be, can we design enzymatic moieties or catalysts that mimic enzymes in order to actually design catalysts that would decompose other polymers like nature does for cellulose. And we did some methods or work related to this in thinking about, can we predict enzymes that would work on reactions that are not their native substrates? So can we use machine learning methods in order to rank the catalytic potential of enzymes for some substrate that would undergo the right transformation based on the enzyme's action, but natively it is not the enzyme's preferred substrate? And that's what's shown here. That is, we did a regression of a bunch of different factors that would predict whether the enzyme would have catalytic potential for non-native substrates. And we were able to make some prediction about enzymes that would work. And now this gets you thinking about, so I mentioned machine learning, this gets you thinking about, well, maybe I don't need that atomistic scale modeling. Maybe I really just need data science. It's very hot right now. Let's just use data science and machine learning methods in order to get rid of the kinetic modeling because all the information is out there. And so that's really gives me a chance to talk about work that we're doing related to bioprivileged molecules. The concept, as Brent Shanks espouses, is that nature is good at doing some things, so it will make certain molecules, but then chemical catalysis is good at doing other things very selectively. So can we find those molecules, these bioprivileged bioprivileged molecules in the middle that we can then use chemical catalysis on to some product of interest? So we had a lot of history in CBERC, which was a NSF ERC that Brent directed, where they actually came up with some bioprivileged molecules. But it took a long time. That is, they kind of almost, and Brent will admit, serendipitously stumbled upon this triacetic acid lactone, TAL, as a bioprivileged molecule. So the conversation went like, biology said, well, I can make you whatever you want, so just tell me what you want. And then chemical catalysis said, well, we can convert anything, just tell us what you're going to make. And they really could never get on the same page as far as, well, all right, let's focus on one molecule, and TAL emerged from that conversation. So he came to us and said, well, can the discovery of these bioprivileged molecules actually be accelerated using computational approaches? And that's where we got involved. And this really, we were inspired by these surveys of top 10 or top 20 platform molecules where people had gone in and said, let's rank these molecules according to their potential to be diversified to a wide variety of different compounds. And they ranked them on a somewhat of a qualitative scale, plus, on a number of different categories. And so we said, can we use our computational methods in order to quantitatively rank molecules according to a variety of metrics that are akin to these qualitative categories? So how many literature reports are there? Is it a commercial product? its platform potential. So how much can it be diversified by conventional catalytic chemistry? So we started using methods basically build on the same foundation that I talked to you about in the earlier part, that is these reaction networks that are going to unfurl all of the different possibilities that these molecules can undergo. So we'll have some set of candidates. We will then query them against databases for a variety of properties so that we can tally those plus, all of those different categories. But now we need also its diversification. That is, what if I have this molecule and given conventional catalytic chemistry, what is the sea of molecules that could potentially be made from it? And that's going to, through these reaction network approaches. So we needed somewhere to start. So you could consider the universe of possible molecules. We decided to kind of develop the methods based on molecules that we would expect that biology would be able to make somewhat easily. So we started by just looking at all the C6HXOY molecules. So we're going to go to a database, the PubChem database, get all the C6HXOY molecules, and we're going to rank them according to their bioprivilegedness. That's not a good. Okay, so let's go get all the C6HXOY molecules. That is 29,252 molecules. So lots of possibilities there. We really didn't want to make 29,252 reaction networks, so we decided to narrow this list down a little bit first. So we developed a reactivity index approach as a proxy for the full reaction network. So if you imagine these molecules, they have certain functional groups. Well, those functional groups get transformed into other functional groups based on some catalytic action, and then that functional group can undergo its transformations based on the defined catalytic action. So we're going to use data science methods, just tallying cheminformatics based on these moieties, reactive moieties in a molecule. You now imagine a recursive sum that says this molecule makes these products, those products now have these moieties, they can make these products with these moieties, so you can imagine the recursive nature of it. And I'll just have one number that represents the platform potential of a molecule. I'm going to compare that against benchmark molecules because I need to design that into some what is a good number, and then we narrowed that list down to 4,600 molecules. Now we're going to take our network generation approach, all the reaction operators that define catalytic chemistry, and generate a full reaction network. So now we'll know explicitly what products are formed from the molecule and its progeny, and we can really look at then the potential of these various molecules. So that's this diagram here. And here is the answer. So in the end, we rank the molecules. These are listed according to their PubChem ID, so that you could go and get every one of these molecules and start looking at it for its platform potential. But there are some familiar faces there. So certainly there are some molecules on which the methodology was trained. Tau, thank goodness, emerged as one of the ones that we're looking at, and also the kumalic acid emerged as a new candidate that the team had already been thinking about, but the method was not trained on. Okay, so just to wrap up in terms of a different way then of thinking about all of this, I've taken you through very detailed atomistic scale modeling with quantum chemical calculations and reaction networks built up from elementary steps. And then we took a detour and said, well, let's use data science methods to just start looking at potential molecules. The question is whether or not we really need all that atomistic scale information and that detailed kinetic modeling. And so I'll pose this as, I think there's a tendency that people want to say data science and machine learning is going to usurp the kinetic modeling. And so that's very worrying to me, given that that's what we mostly do. So the idea would be that we have the reactants and the reaction conditions, and we have the products that we're interested in, and I don't really care how we got there. We just need a black box in order to look at that. And so this idea of neural nets is one possibility of the black box, that you can train a network in order to then very quickly give you an answer about the connection between inputs and outputs. And so I'm going to choose an example from Jim Fentner's group at the University of Washington, where they did a very nice example related to lignin decomposition. So they were looking at how lignin degrades under pyrolysis conditions. And so the inputs would be things like temperature, heating rate, how much carbon's in the feed. That we saw that this lignin is a diverse molecule, but it's got carbon and hydrogen. And then we have a bunch of outputs we want to predict. So how much CO2 would be made, how many heavy aromatics, et cetera. And so they did a detailed description of the connection between the inputs and the outputs by looking at a variety of network architectures, a variety of how many inputs and outputs I connect simultaneously, the very detailed analysis of that. And they were able to come up with really a very nicely trained neural network that was able to correlate the output values with the input values. And that's shown here by some examples with a line of parity giving you a sense of the ability of the model in order to capture the data. So this is not looking good for kinetic modeling. Because this was a 3 to 4 order of magnitude speed up compared to the detailed approach I talked about in the beginning with these ODEs and solving elementary step kinetics with very stiff timescales. And so this would be very attractive for what Paul talked about yesterday in terms of embedding into a reactor scale model that also has a number of other complicated features. But there was one step in the process here that I didn't really admit to you up front, which is how did they get the data to train the neural net? It was from a kinetic model. So they actually ran the kinetic model many, many times with 250,000 combinations to cover this input parameter space. And so then it was really this need for a large amount of data to have any chance of training doing the machine learning method that kept the kinetic model intact. So I just hope to give you an overview of the kinds of methods that can be leveraged of problems that we're thinking about in this workshop, where we can use very detailed reaction path analysis to predict product distributions. I did not talk about the upper right much, but this was this idea of kinetic Monte Carlo to do novel architecture design of polymers, this idea of bioprivileged molecules, in order to maybe make some predictions about new monomers, new polymers, new flame retardants. And then finally, we have to acknowledge that machine learning is a companion in all of this, but whether that can be used without some synergy with a detailed atomistic view, that it depends on the data that's available. So. Just like to thank collaborators and also funding agencies, and if there's time, happy to take a couple questions.
I have time for one question. Yeah, sure. Yeah, maybe turn the mic on, yeah. Turn the mic on, yeah.
No? So when you talk about artificial neural networks, one of the problems that you have, it actually you sort of mentioned, is actually the paucity of data that we have to actually train the things, right? That's one. And the other one is actually when you train the things for different classes of chemical reactions, you're going to have to use probably different kind of descriptors. Could you tell us a little bit more about how you envision this in these things? Because I do believe that it has to be a connection between the detailed kinetics and the machine learning techniques. That's the only way around it.
Yeah, I think that, and I feel like John Kitchen at CMU has a very nice perspective on the confluence of machine learning methods with fundamentally based models, because I have seen some evidence of machine learning models that then violate fundamental physical principles that we all know. And so I think that's the danger of them. You touched on that, yes, you need a lot of data. So in that case, the kinetic model provided a nice platform for that. And then in addition, the other part that I think you were also alluding to was the idea of the predictive nature. And so even if you have all this data for the kinetic model, train the neural net, then it can't capture anything outside the regime in which it was trained, whereas that's the value and the beauty of these fundamental kinetic models, is that they can predict outside those conditions. So, yeah, provide some caution.
Okay, let's thank Linda. Yeah, I think we should postpone that. Okay, yeah.
Okay.